Kia ora and welcome to another online tutorial. Today we're going to be talking about simple harmonic motion. Specifically, what is simple harmonic motion? What are the requirements of simple harmonic motion? Why a system that is experiencing simple harmonic motion will maintain a constant period even though our displacement of either the pendulum bob or mass on a spring changes or decreases over time. As well as looking at a system like a bungee jump and comparing that to simple harmonic motion and explaining why that isn't simple harmonic motion. First off, what is simple harmonic motion? Simple harmonic motion, or SHM, is a special type of motion observed in oscillating springs and pendulums, where they have what is said to be a restoring force. A force that is always trying to return the mass or object to its equilibrium or central position. And that force gets greater as our displacement gets greater. Meaning that our force is proportional to our displacement, which we put here. Seeing as force is proportional to displacement, that also means that the acceleration that a mass or object experiences in the system is proportional to its displacement from the equilibrium, meaning that an object that is further from its equilibrium will have an increased force, meaning that it will also have an increased acceleration, while this restoring force perpetually acts towards the equilibrium. It's important to note, and hopefully you've observed this from level 2 physics, is that our period does not change when our displacement changes. Using our example from here, which is a simple pendulum formula, in level 2, it is okay to say, oh, it doesn't change because it's not in the formula. But we're going to look as to why that actually is and how that ties into the theory. What are the requirements for simple harmonic motion? It's just that our restoring force is proportional to displacement and that our restoring force acts towards equilibrium. So in a system where we're experiencing simple harmonic motion, why will we have the same period irrespective of the amplitude or displacement of our pendulum or mass on a spring? We have already stated that if, our restoring force is proportional to d, our displacement. In time, as our displacement decreases, because these two are proportional, the force will also decrease. If our force decreases, force additionally being proportional to our acceleration, as our force decreases, our acceleration will also decrease. So as the displacement becomes smaller, the force acting to the equilibrium is smaller, meaning that our acceleration is less. So the object will accelerate slower, meaning it will complete the oscillation at a slower rate, but because the displacement is now smaller and that these things are proportional, the time or period of such is the same. So we've expanded on why displacement is not in our equation. Let's talk about why an action like a bungee jump isn't simple harmonic motion. When an individual doing a bungee jump is in free fall, the forces acting on our individual is constant. This is not a restoring force. This is our weight force, and it is acting constantly in the same direction toward the center of the earth. It is not acting toward our equilibrium. So we have an inconsistency there, which means we have not met the requirements for standard harmonic motion. After a period of time, when the individual's displacement is at its maximum, the tension force acting on said bungee cord will then act towards what could be referred to as the equilibrium, but this is not constant. So our jumper acts as a mass, our force due to weight is acting downward, not towards equilibrium. Therefore, we have not met the requirements. Once the band is stretched out, he will behave like a mass on a spring and return. He will not, or they will not, go past and then repeat the cycle. Therefore, they are not moving about our equilibrium. Our force is not proportional to displacement, and we have not undergone simple harmonic motion. Hopefully that's helped, team. Hopefully you can use this to get out there and do some physics. Have a good day and good luck.